Hello everyone. Today we're going to be solving the problem longest palindromic substring. So, given a string S, find the longest palindromic substring in S. You may assume that the maximum length of S is 1000. So the input here is BA, BAD, and the output should be BAB or ABA. So what exactly is a palindrome? A palindrome is a string that is the same forwards as it is in reverse. So if we look at BAB, we'll see that BAB would be the same if it was spelled forwards or backwards. So if you're ready to solve this problem, I encourage you to try it on your own first, but if you're ready to get started, come with me to the whiteboard. So to solve this problem, we're going to use the idea of expanding around the center of a palindrome. As you can see here, I have two different types of palindromes. One of these is an odd length palindrome, and the other is an even length palindrome. So to expand around the center, we need to define exactly what the center of a palindrome is. So if we look here at the odd length palindrome, the center of this palindrome is B. And if we expand from this center out, we can check to see if the characters on either side that are mirroring each other are equal. And if they are, we can increase the length of our palindrome. In the odd length palindrome, the center of a palindrome is an individual character. But in an even length palindrome, we can see that the center is not a character, but is the space between two characters. So the center in an even length palindrome would lie here between these two characters, these two B characters. And to expand around the center, we would expand from between these two characters, checking to see if B and B are equal. They are, and expand again to check to see if A and A are equal. They are, and increase the length of our palindrome this way. So now that we know how to expand from the center and check for the size of a palindrome, let's go through a quick example of using this strategy to solve this problem. To solve this problem, we're going to initialize a result to 0, and we're going to iterate through this string, checking each character and the space between the characters for the center of a palindrome. We're going to keep track of our longest palindrome and then return the length of the longest palindrome at the end. In this problem, we're just going to be tracking the total length, but you could see that using this algorithm, you could easily adapt it to returning the string, which is what the prompt in the question is asking. So if we check A first, we see that A is itself a palindrome, and we try to expand out. We can't expand out because B is not equal to nothing out here. So we will update our palindrome length to 1 for A and check the space between A and B. These two are not equal, so we cannot update our palindrome. Checking B, we see that it is a palindrome of length 3. So we will update our result to 3 and check the space between A and B. A and B are not equal, so we cannot update the length of our palindrome. We'll now check A and see that it is a palindrome of length 3. We already have a palindrome of length 3, so we will not update. So now we'll check the space between A and B and see that once again, they're not equal, so we cannot update. We'll check B, and we'll see that B is a palindrome of length 1, but when we try to expand from B, A and B are not equal, so we will not update our result. We'll now check the space between these two characters, these two B characters, and we can see that it is actually a palindrome of length 4. So this is the longest palindrome we've seen to this point, so we can update our result to 4. We'll now check this B character, see that it is a palindrome of length 1, try to expand from the center, and we'll see that B does not equal A, so we will not update our result. We'll check the space between A and B, and we'll see that A and B are not equal, so we will not update our result. Finally, we will check A, and we'll see that A is a palindrome of length 1, but when we try to expand, there's nothing to compare it to on the right side of A. So A is a palindrome of length 1, we will not update our result. So as you can see, using this strategy, we have found our longest palindrome, which is A, B, B, A. So you could see that just by keeping track of the indexes where you found the palindromes and the length of the total palindrome, we could return this string at the end, which is what the prompt is asking you for. And that is the n-squared algorithm to solve this problem. Let's go over quickly why this is an n-squared algorithm. So why is this an n-squared algorithm? This is an n-squared algorithm because at each point that you're checking for a center, and in this particular string, there are no even length palindromes, so we will only check the individual characters themselves. but you could see that at each point where you're checking for a palindrome, you are potentially having to expand all the way to the edge of the string. So let's start by checking A. So we check A for palindrome as a palindrome of length 1. So we only expand to the edge of this side of the string. Now we check for B, and we see that B is a palindrome of length 3. When we check A, we see that A is a palindrome of length 5. We check B, we see that B expands the entire length of the string. We check A on the other side, and we see that it is a palindrome of length 5. And we check B, and we see that it is a palindrome of length 3. And then A, finally, a palindrome of length 1. So at each iteration through this string, we're expanding all the way to the edge of the string. So you could see that as this string grows, if we have this pattern or this type of palindrome, the time complexity of this problem would increase by some factor of n. And that is why this is a n-squared algorithm.
So now that we've solved this problem using the idea of expanding around a center, what other information is available to us to optimize this algorithm? So there are two ideas that I want to cover here, and they are the idea of what information does the center of a palindrome give us, and also the idea of using a mirror image, right? So the center of the palindrome, so this array right here, this whole entire array is a palindrome, and its center is B. And this is one side of the palindrome. This is the mirror side to this side here. So we could think of it like as we've started calculating these palindromes, this left side over here is the side that we've already calculated, and then this right side here is the side that we can use the information from the left side so that we don't have to solve the same problem twice. So let's go ahead and fill these values in and talk about the ideas behind using the center and the mirror. So this is a palindrome of length 1 at this position here. And then this is a palindrome of length 3 around B. This here is a palindrome of length 5 around A. And then finally, this is the palindrome of the entire array here, and it's of length 7. So what information is available to us? So what I want you to think about this center as is at any point where we've defined that this is the center of a palindrome, after we've calculated this palindrome, so we've just calculated that this palindrome extends the entire array, this is how far I can see, right? So you can see all the way out to here, and you can see all the way out to here, right? You've already looked at all of this stuff. So we don't need to expand around the centers on this right side again, because we've already expanded out to this side, right? So this is the right barrier, and this is the left barrier. So if we use the idea of a mirror, so this A here, its mirror is at this position here. So we can just go ahead and fill this in. This is 5. And then we look at B, we see B's mirror is 3. And then we look at A, we see A's mirror is 1. Now this works because the center that we've defined here encompasses the entire array. But what would happen if we had another character over here? How could we then use the information of a mirror to update these values? So let's take a look at that next. So I've gone ahead and added an extra character off to the right here. So the center that we've defined is still here around B. So where we can see extends from here to here. We can't see beyond this A here because the current palindrome centered around B is of length 7, which encompasses this whole portion of the array. So I'm going to put a line here. This is the right barrier, and then this over here, this is the left barrier. So what assumptions can we now make? So if we look over here, we see its mirror is 5. And we don't want to just put 5 down here, right? Because we want to be able to potentially include anything that's outside of this right barrier. So what can we say about this mirror position here? What information can we extract? Well, what we know is that this palindrome here around A is completely contained within this, this overarching palindrome that we've defined as the center around B. So we know that this palindrome is greater than or equal to 5, right? Because this palindrome is here is 5, so we know that this palindrome also here must be at least 5. Similarly, we can say the same for B, that it's greater than or equal to 3 because its mirror is 3. And then we can also say that this one is greater than or equal to 1, A, on the outside here. So how does this information help us? Well, if we know it's greater than or equal to 5, we don't have to start expanding from the center here, counting things that we've already counted. We can just start expanding from out here. So we can take a look at this B here and this B here. We can see that they match. We can try to expand again. They don't match. So we know that this palindrome centered around A is actually of length 7. Similarly, we can look at B. We know it's at least of length 3. So we don't need to look at any of this. We can just start looking here. We see that these B's match. We try to expand again. They don't match. So we know it's of length 5. And then we look at A. We know it's at least of length 1. So we can automatically just look beyond itself. And we see that those match. We try to expand again. They don't match. We know it's of length 3. And then finally we'll get to B. And this is the end. So we try to expand from B. We have to expand around B because it's not contained within the center. And we see that it's just of length 1. So now that we know how we would use this information expanding to the right with palindromes that are completely contained within the center, let's look and see what would happen if we took this B and we put it on the other side. So I've moved this B to the other side, and the barriers are now from this right side here to this left side around this center that's centered around B. So let's fill in these palindrome lengths. So this B here is a palindrome of length 1. We can see that A is a palindrome of length 3. We can see that B here is a palindrome of length 5. A is a palindrome of length 7. And then B is still this overarching palindrome that we've been working with, and it's of length 7. So now what can we say? Well, if we look at A, it's a palindrome of length 7, but we can't say that A is a palindrome of length 7, right? Because A here expands beyond the center that we're currently looking at. So remember what we said earlier, that the center is how far we can see, right? So if we can only see to this left edge, and we know that A extends beyond that left edge, then we know that its mirror extends all the way to the right edge. So we know that A at least encompasses these two characters all the way up to the right edge. So how could we dynamically update the sizes of this mirrored side here? Well, what we know is if we're looking across the center at a mirror value, we know that the size of the current item, A, that we're looking at is equal to the minimum of its mirror and the right boundary minus its current position, right? So the distance between itself and the right boundary. So that is 7, and then it extends to these two characters, which means it also includes these two characters. So that's a length of 5. So we know that it's 5. So we can fill in 5 for A. And now for B, we see that B's mirror is 5. And its distance is 1, which means it incorporates both of these characters, which is the size of 3. So B is a minimum of 5 and 3, which is 3. And then finally, we look at A. There's no characters between itself and the boundary. So it just includes itself, which is of length 1. So its mirror is of length 3. And then itself is length 1. So we then update this to just be 1. So this is the entire concept of this problem. The only piece that we're missing now to solve this in n time is how do we update the center as we're iterating through the string. So let's take a look now at how we would use this as we iterate through a string. Let's do a run through of this algorithm. So you'll probably have noticed that there are a lot of hash marks in between all the characters in this string. And the reason for the hash marks is it makes it easier both in code and just visually to check the spaces between the characters. So the hash marks inside of this array represent the spaces between the characters, and we'll be checking them as we increment through. So there are 3 things that are happening at every iteration through this algorithm. The first one is we're checking to see if the current position is less than the right barrier. If the current position is less than the right barrier, then we can use its mirror to update its palindrome. Then we need to expand around the center. So we'll expand around the center to measure the size of the palindrome. And then finally, we need to check to see if the current palindrome that we just measured, if it expands beyond the right barrier, then we need to reassign the center. So just follow along with this algorithm and just try to follow along with what's happening, and I think you'll start to understand how this algorithm works. So we'll start at position 1, and we'll see that position 1 is outside of the right barrier, so we cannot use its mirror to update its palindrome. So we'll expand around the center. We'll see that we can expand once, so we'll put a 1 in for that position. We'll check to see if we can update the center. The current palindrome expands beyond the right barrier, so we'll update the center and the right barrier. The current position does not lie within the right barrier, so we cannot use a mirror to update its palindrome. We'll try to expand around that position at index 2. We'll see that we can't expand around that position, so we'll put 0 in for its palindrome. We'll increment our pointer to index 3, and we'll see that index 3 is outside of the right barrier, so we can't use a mirror to update its palindrome. We'll expand around B. We'll see that we can expand once, twice, 3 times, so we'll put 3 in for the palindrome for B. We'll check to see if we can expand if we can update the center. The current palindrome expands beyond the right barrier, so we will update both the right barrier and the center. We'll increment to index 4, and we'll see that now at index 4, there is a mirror across the center that is at index 3. So we can use its mirror because we are within the right boundary to update index 4's palindrome. Its mirror is a palindrome of 0, so we'll update it to 0. We'll try to expand around that palindrome, and we'll see that we cannot expand. We'll check to see if we can update the center. It does not expand beyond the right boundary, so we cannot update the center. We'll increment the pointer and move the mirror. We're still within the right boundary, so we can use the mirror to update. We'll update index 5's palindrome to be 1. We'll try to expand around that palindrome. We'll see that we cannot expand around it. We'll see if we can move the center. The current palindrome does not expand beyond the right barrier, so we will not update the palindrome. We'll increment our pointer, and now our pointer does not lie within the right boundary, so we cannot use a mirror to update its palindrome. We'll try to expand around index 6, and we'll see that we cannot expand, so we will put a 0 in for its palindrome at index 6. So we'll increment our pointer to index 7. And index 7 is not within the right boundary, so we will expand around index 7. We'll expand once, twice, 3, 4, 5, 6, 7 times. So at index 7, there's a palindrome of length 7. The current palindrome expands beyond the right boundary, so we can update the right boundary and the center to be around index 7. We'll now increment the pointer to index 8. Index 8 has a mirror at index 6. Index 6 palindrome is 0. So we can use index 6's palindrome to update 8. We'll update 8 to 0, and we'll try to expand around index 8. We cannot expand around index 8. We'll also try to update the center. We'll see that it does not expand beyond the right boundary. So we will not update the center. We'll increment to index 9. Index 9 has a mirror at index 5. We can use index 5's palindrome to update index 9. We'll try to expand around index 9. We cannot expand farther. We also cannot update the center because index 9's palindrome does not expand beyond the right barrier. At index 10, its mirror is at index 4 and its palindrome is 0. We can use its palindrome to update index 10. We'll try to expand. We cannot expand. So we'll increment our pointer to index 11. Index 11 has a palindrome. Its mirror's palindrome is of size 3. So we can use the palindrome at index 3 to update index 11. So we will now start 3 spaces away and expand beyond its mirror's palindrome. So we see that we can expand to a size of 4, 5, 6, 7, 8, and 9. So we started with a palindrome of its mirror that was of size 3, and we expanded beyond it to a palindrome of size 9. So we'll now update that position to be a palindrome of size 9. We'll see if we can update the center. The current palindrome does expand beyond the right boundary. So we will update the right boundary and we'll update the center. So we'll move to index 12 and we'll use its mirror to update it. It's 0. We cannot expand farther and we will not update the center. So we'll move to index 13 and we'll use its mirror to update it. We'll try to expand beyond it. We can't. It doesn't expand beyond the right boundary, so we will not update it. We'll increment to index 14. We'll update it with its mirror. We'll try to expand. We'll try to update the center, and we cannot. So now we're at index 15, and index 15's mirror at index 7 is of size 7. It expands beyond the left boundary. Because it expands beyond the left boundary, we cannot just update it with its mirror. We have to use this equation down here that says that its boundary is the minimum of the distance between itself and the right boundary in its mirror. So its mirror is of size 7, and the distance between itself and the right boundary is 5. So we will update it to 5. We'll try to expand around that center, and we'll see that we cannot expand any farther. We'll also try to update the center. We'll see that its palindrome does not expand beyond the right boundary, so we will not update the center. We will use index 16's mirror to update it. We cannot expand farther, and we will not update the center. We will use index 17's mirror to update it. We cannot expand any farther, and we cannot update the center. We'll use index 18 to mirror also to update it, and we also cannot expand, and we can't move the center. So now at index 19, its mirror has a palindrome of size 3. It expands beyond the left barrier. So we take the minimum of the distance between itself and the right boundary and its mirror, which is 1. We'll try to expand beyond 1, and we'll see that we cannot expand any farther. And it also does not expand beyond the right boundary, so we will not update it. We will not update the center. We'll increment to index 20, and it does not lie within the right boundary. So we will try to expand from index 20. We'll see we can expand once and twice. And this is the first case where we've seen a center of a palindrome that lies between 2 characters, which is on a hash mark. So you can see that at 19 and 21, we added 1, we incremented 1 so it was a size 1, and then the hashes match on 18 and 22, so we add another 1. So the palindrome at index 20 is of size 2. The palindrome does extend beyond the right boundary, so we will update the right boundary and we'll update the center. Index 21 has a mirror, and it does lie within the right boundary, so we will update it with its mirror, and we will try to expand. We can't expand any farther, and we also cannot update the center. And finally, we're on index 22, and it lies outside of the right boundary, and we'll try to expand. We cannot, so we'll fill in a palindrome of 0. So now we've incremented all the way through, and you can see that the largest palindrome lies at index 11. So we can iterate through the lengths, or we can also keep track as we go of what is the maximum palindrome that we have seen, and return that index, and we can extract the longest palindrome from this string. So there's one important takeaway that I want you guys to have, and that is, why is this an order n algorithm? Well, the reason why this is an order n algorithm is because at each stage we expand right, and we never look back. We just keep expanding right and expanding right and expanding right, and we never recalculate anything that we've seen behind us. So at most, we're looking at every individual index twice, because we're looking at it once as we expand, and then once as we increment across it. So the time complexity of this algorithm is of order 2n, which is, if you drop the constant, it's just order of n. So let's take a look at what this algorithm would look like in code. To code this problem, we're going to use 2 helper functions, and then this longest palindrome function to handle the logic of actually implementing this algorithm. So the 2 helper functions are insert hash and get palindrome length. Insert hash is just going to insert the hashes between all the characters and return an array to us that we can use to iterate over all the characters and the spaces between the characters. And then get palindrome length is going to be the function that we use to actually expand around the center of every individual palindrome. So for insert hash, we will create an array, and then we will loop over the string. So for every character, we're just going to push in a hash mark as well as that character. And then we'll need to push in one more hash at the very end. And then we can just return the array. So that will give us the array with hash marks between every individual character. So the next thing we're going to need to do is define how we're going to expand around the center. So we'll define 2 variables, start and end. So for the start is just going to be that current index, and then we will want to subtract the length. So we're going to pass in the length, which is just going to be the size of every palindrome as we're iterating at that current index. So we will want to start counting however far away from the center the current size of the palindrome is, and then we will also want to subtract 1 for the case that the current palindrome has not been measured yet. It's of size 0. We'll just start 1 index away from the character center. And then we'll do the same thing for the end. We will, except we'll go in the positive direction, the length plus 1. So we will say, we'll do some bound checking here, and we'll say that if the array at start and the array at end, if those positions exist, then we can measure the palindrome. So if the start character equals the ending character. Then we can increment the length. If it does not equal, then we want to break out of this while loop. And we can also decrement the start and increment the end after every time we compare the two characters. And then we'll just return the length at the end. So that should take care of those two helper functions. And now we'll code out the logic for actually implementing the algorithm. So we'll want to first create the array from the string. So we can use our insert hash function passing in the string, and then we'll also want to initiate that lengths array. So the lengths array, we will just create an array that is the same size as the string array, and we'll fill it with zeros. So that will just initiate every palindrome to a size of 0. And now we'll just need variables for the center of the palindrome. We are also checking the right boundary, and we're also going to track the max index, right? So the index of the currently largest palindrome that we've seen to this point. So now that we have these three variables, we want to start looping over the string array. And we can actually start at the first index. So we're going to need to keep track of the mirror. So the mirror is the mirror to the current position on the other side of center. So we'll create a mirror variable that is equal to the mirror of the current index. So that would be 2 times the center minus the current position. So this is going to give us the size of the palindrome on the other side of the center that is the mirror to the palindrome at I. So now we just need to go through the process of checking the three things we checked earlier. So the first one is just going to be if I is less than the right boundary. If I is less than the right boundary, then that means that we can update the current palindrome size to be that of its mirror. So we can say that length I is equal to the minimum of the mirror of the mirror and its distance from the right boundary. So right boundary minus I. And now that we have updated the palindrome at that position, we can now try to expand. So we'll say that the current length at I is equal to the helper function that we defined. So get palindrome length, and we will pass in the array, the current index, and the current size of the palindrome. And this will update, and this will expand around center for the palindrome at that position. So now we just need to check to see if the current palindrome that we just measured, so that's going to be I plus the size of the palindrome. If that is greater than the right boundary, then we need to update the center to be the current index, and we also need to update the right boundary to be the current index plus the size of the palindrome. So that's just going to be lengths at I. So that should take care of all the logic of tracking center, updating the palindrome, and now we also need to just check to see if the max index is less than the current palindrome. So if the size of the max index, if that's less than the current palindrome, then we need to update max index. So max index will now be I. So that should be all the logic we need for tracking the palindrome. So now all we need to do is just extract the palindrome from the string and then return it. We also, I forgot to initialize these to be 0. So we can, just for clarity, we'll define the starting index and the ending index for the string. So the starting index is going to be equal to the max index value minus the length of that palindrome. So that's lengths at max index. And then the end is going to be max index plus the lengths at max index. And now finally we can just return the string. So we'll return the slice of this string. So that's the start to the end plus 1. And then we'll filter out all of the hash marks. So we just say that as long as it's not equal to a hash, we'll accept that string or that string character, and then finally we'll just join it together. Okay. So just for a recap, we initialized an array with the hash marks in between. Then we created an array for tracking the palindrome lengths, and we set each index to 0. We created variables for the center, the right boundary, and then a variable to track our current max index. And then we looped over the string, keeping track of the mirror. And if the current position was less than the right boundary, then we'll update the length to be the minimum of the mirror and its distance from the right boundary. We'll try to expand from center here using get palindrome lengths. And if the current size of the palindrome is greater, expands beyond the right boundary, then we update the center and the right boundary. If the length of the current max index is less than the palindrome that we just measured, then we'll update the max index to be I. And then finally, we're just taking the slice of that portion, and we're filtering out the hash marks and joining it together. So as you can see, I have already ran this, but let's go ahead and take a look at some of the results. So here's where our code ran, and what I actually want to go through is the n-squared version of this algorithm. So let's check out someone's version of that. Okay, so here's an n-squared version of this algorithm. So right here, this is a function that is called expand palindrome. And it just takes in 2 index, so left and right indexes for the center of the palindrome. And they're just expanding right here. As long as the characters are equal, then they increase left and right. And they'll just, if they're just tracking max right and max left and reassigning them to be equal to right and left if the size of right minus left is greater than the size of max right minus max left. So they're just tracking to see, okay, what's the largest palindrome I've seen to this point? And they're just expanding around the center. So here they're just looping through the string, and what they're doing is they're checking to see if the character I is equal to the character plus 1. So if there are 2 characters that are equal to each other, then that's a potential point to be expanding around between 2 characters. So the only place where you can have a palindrome that's between 2 characters is when you have 2 characters that are equal to each other. So they're checking for that. And if that's not the case, then they're just expanding around, passing in I at the same index to just expand around a single character. So why do I want to talk about this? I want to talk about this because while this algorithm here sacrifices time, so we solved it in n time, this is n-squared time, but we also used n space, right? Because we had to, at each index, we had to track the size of the palindrome. We had to keep track of all of the indexes for those palindromes in another array that was equal to the size of our input. So while our algorithm solved it in n time, we also use n space, whereas this algorithm here solves it in n squared time, but uses no extra space, so constant space. If you made it all the way through this video, congratulations. I know it was another long one. Hopefully we'll do some easier problems that will be a little bit shorter. But if you solved this problem on your own, congratulations. If you made it all the way through and you understand this algorithm, it's actually a really complicated algorithm. So if you understand it, then congratulations. If you coded it yourself, then kudos to you. There's no way I would have been able to just come up with this solution on my own. And if you want to look into this algorithm further, it's called, I believe it's called the monikers algorithm. So it's actually a pretty famous algorithm for solving this particular problem. If you want to read into it further, then to get a better understanding, then you can Google search that and check that out. Anyways, I hope to see you on my next video. And again, congratulations if you made it all the way through.